Hello everyone, I am Arvinda from Group 72 and today I'll be presenting our project Store Demand Forecasting using time series and neural networks. Demand forecasting holds a pivotal role in supply chain management and retail operations. In the context of retail stores, precise demand forecasting is crucial to ensure the right product quantities are available at the correct time and location, thus preventing stockouts or overstocking. This is where neural networks and time series forecasting techniques play a substantial role in addressing the challenges of demand forecasting. So in this project, our main goal is to develop a cutting-edge forecasting model leveraging advanced machine learning algorithms and sophisticated time series analysis techniques. By harnessing the power of data-driven insights, this project aims to revolutionize sales forecasting, empowering businesses to optimize inventory management, streamline resource allocation, and maximize profitability. As we discussed, we can see that demand forecasting helps in improved planning, efficiency, better service, enhanced performance, and a competitive advantage for the retailers. Now, these are some of the related works. So this slide provides an overview of a data source and its attributes. We obtain the data from the Store Item Demand Forecasting Challenge dataset available on Kaggle. The dataset includes four key attributes, which are date, store ID, and sales, representing the number of units sold. In total, there are 10 stores and 50 items included in the dataset. Sales were recorded across 10 different stores for 50 different items from January 1st, 2013 to December 31st, 2017. This is a subset of our dataset obtained from Kaggle as mentioned earlier. Next, we have our data pre-processing step. So in this step, we verified the absence of duplicates, ensuring the data integrity is present. We standardized date formats for consistency and conducted a thorough check of null values, guaranteeing data completeness. Despite weak correlation with sales, we opted for an inclusive approach incorporating all attributes to capture potential interactions and dependencies, enhancing our model efficacy. Finally, data was sorted chronologically with a 75-25 train test split for robust model evaluation. Now this is a pie chart of our train set exhibiting a balanced data distribution across different years, indicating no significant data imbalance. Now this uniform distribution ensures that each year is adequately represented in our training data, enhancing the robustness and reliability of our model across various time periods. Next, we have our pre-processing and data transformation step. So in this step, the date variable representing the scheduled departure times was converted to a discrete ordinal attribute for the model to interpret it as an independent variable and capture temporal dependencies. Similarly, the store and item variables were also label encoded, since the one-hot encoding approach proved to be a little inferior compared to the label encoding approach. Now, these are some of the tools and technologies that we used in our project. Next, we chose advanced time series models like BiLSTM, LSTM, and CNN, BiLSTM, and CNN for their ability to capture complex temporal patterns. Alongside these, we included baseline regression models such as random forest regression, XGBoost, artificial neural network, etc. So the LSTM and BiLSTM were highlighted for the strengths in handling the vanishing gradient problems and capturing long-term dependencies. So we anticipated a superior performance from these time series models, especially the LSTM and its variants. Next, we have a list of our baseline models, which include random forest, convolutional neural networks, XGBoost regressor, and ANN. Followed by which we have our time series machine learning algorithms, which include long short-term memory, which is LSTM, ARIMA, and bidirectional LSTM. Finally, we have our ensemble models that we built from scratch, which include LSTM and a CNN hybrid, as well as a bidirectional LSTM and a CNN hybrid model. This slide showcases two models, a traditional LSTM model on the left and a hybrid LSTM model on the right. The hybrid model developed from scratch combines CNN and LSTM components. In this architecture, the CNN segment convolves over the input data, extracting spatial features, while the LSTM captures temporal dependencies. Both pathways then undergo dense layers for feature refinement before their outputs are combined for accurate prediction or classification. We also hand-tuned each of these models, and a batch size of 256 and Adam optimizer proved out to be suitable for training. BiLSTM CNN, which is one of our other models, also has similar architecture in which each LSTM layer is surrounded by a bidirectional wrapper. So when it comes to training and evaluation metrics, we use mean square error for our model training and testing. So this graph illustrates the mean square error obtained from our baseline models. As we can see, CNN model performs the best, followed by MLP and XGBoost. Contrasting that with our time series approach, we can see that the BiLSTM CNN hybrid, which is our model, performs the best on both training and testing sets, closely followed by the BiLSTM and LSTM CNN models. Although our model has a slight improvement compared to the traditional BiLSTM model, it is still noteworthy. Finally, we can see that the BiLSTM plus CNN model demonstrated the highest sales prediction performance compared to the other models. However, limitations such as limited attribute coverage and lack of granularity in the dataset may have hindered capturing crucial factors like promotions or seasonal trends, potentially reducing the predictive accuracy. Future improvements may involve advanced evaluation techniques for temporal dynamics and acquiring additional dataset information. These are some of our references, and thank you for your time.